Okay, so here's a quick look at the level 2 mechanics paper from today. Let's get straight into it. So 1A, I won't read the question just to save time. You can pause the video if you want and read it. And I don't guarantee the answers to any of these questions. This is just my first run through. So the force on the dog should be towards the center, and I would label that as centripetal force. Okay, this is quite good because it's already given us the values laid out almost like the guess method that I would use. And then what we're trying to find is the radius, so that's our unknown. So we're using Fc equals mv squared over r. And so r is equal to mv squared over Fc, which is 10 times 0.87 squared divided by 15. Excuse my writing. And that should come out as 0.5046 meters, more or less. And so I'll probably be rounding that to 2 sig figs. The 10's a little bit iffy as to whether it's 1 or 2, so presumably it'd be okay either way. Not that significant figures are marked unless the question specifically states it. So I'll probably go just out of force of habit, something like that. Common sense check, yeah, that probably fits with a round table shown in the picture. Then we've got a question about slippery patch and the dog sliding off at a tangent. So we're asked to explain the velocity immediately after it starts moving off at a tangent. And so the velocity would begin at a fixed value at and I think that after is really key there. So the initial velocity would be 0.87 meters per second. This would decrease due to friction. So we're not being asked to explain the dog's velocity, how it's changing from being in circular motion to being tangential. We're being asked to to explain the dog's velocity immediately after it starts moving off at a tangent. So it would be immediately after it's 0.87 meters per second in a specific direction. So if this was the dog and it was rotating, say, anti-clockwise, then it's going to slide off something like that. Any frictional force would decrease that velocity according to Newton's second law. So you could state N2, or an unbalanced force acting on an object will cause acceleration. So this next one, we've got time, 2 different times, we've got a mass, we've got a velocity. It's an impact or impulse question, and we'll be looking at momentum for that. So on the first situation, our time is, I'll call it T1, is 2.0 seconds. We've then got a velocity of 0.87. That's assuming it hasn't lost any velocity. Which doesn't sit very well with this previous question, but unless we're expected to assume that there's no frictional force here, but I don't think that would be safe to assume. I don't think it's said, it said it's a slippery patch, it hasn't said that there's no friction, so there would still be some friction which would reduce the dog's velocity. But we're going to use this velocity value anyway. That's the one that we've got. And the mass of the dog is 10 kilograms. And so what I'd be looking at there is that the change in momentum is equal to the mass times velocity final minus the mass times velocity initial. That is 10 times final velocity would be 0 when it's come to a stop, then subtracting 10 times the initial velocity, which is 0.87. And so that gives us a change in momentum of negative 8.7 kilogram meters per second. I would then use the impulse equation, so the force experienced will be equal to the change in momentum divided by the change in time. And so we're looking at, I'm just going to, because I'm not, the negative is indicating direction, I'm just going to use the magnitude of that change. So 8.7 divided by 2.0 should be somewhere in the region of 4.35 newtons. Okay, and then if we were to calculate the force experienced in the non-cushioned collision, then it would be a similar calculation again. The change in momentum is going to be the same, so that's 8.7 seconds, but this time, 8.7 kilogram meters per second, so 8.7, but this time we're dividing it by 0.1 seconds, and so that's going to come out as 87 newtons. So you're comparing 4.35 newtons with 87 newtons, so quite a substantial difference there. In terms of the explanation of that, I would say, since, I would list my formula, change in momentum equals force times time, which I've rearranged to force equals change in momentum over a change in time. The change in momentum is fixed, or, it's consistent between the two different scenarios. Because the mass of the dog hasn't changed, its initial velocity hasn't changed, and its final velocity hasn't changed. So change in momentum is fixed, and a decrease in time of collision results in a smaller force. Decrease in time of collision results in an increase, increased force. Okay. All right. We've got a classic momentum question here. So we've got the basic principle is that the sum of the momentums, so the sum of the momentum before must equal the sum of the momentum afterwards. We know that the combined mass of the dogs is 22 kilograms, and so I'll just note down here that the momentum is equal to mass times velocity. We've got one object after the collision, which has a combined mass of 22 kilograms times 0.3. We're assuming that positive is to the right here. So 22 times 0.3, and then before that we know that 12 times v, so mass times velocity, plus 10 times, because this velocity is to the left, it's going to be negative, so 10 times negative 1.1, and that should all be able to be resolved to give us v. And so that gives us 12 times v minus 11 is equal to 6.6. That gives us v is equal to, that's going to be 17.6 divided by 12, which comes out as 1.47 meters per second. Looking at significant figures there, I'm probably working to 2 sig figs, but again, that's not really important unless the question asks. So I'll probably give my answer as that. It's asked the speed, so it doesn't need direction, but that would have been to the right. Okay. All right, labelled arrows to the diagram above with the flower to show the two forces acting on the flower. This is quite an interesting one. I think that I would give the answer as weight force, and I would then give my upwards arrow, because the flower, I've done that a little bit too long there, so I'll just bring my longer arrow, my downwards arrow down a bit longer to match that. I can also put a little bar on each of those to show that they should be equal in magnitude. I would probably call that support force upwards. I was wondering whether the question was looking for tension. I'm not sure, it might allow either way. But technically I would say that since the flower is resting on the solid material, then the upwards force in this case would be support. Calculate the spring constant for one spring. So we've got each spring has an extension of 0.01 meters. The mass of the flower is 0.11. So the weight force of the flower would be 0.11 times negative 9.8, which gives us... well, I'm going to divide that by 3 because it's being spread out among three of the springs. So that's the weight force on one spring. Weight force on one spring is equal to that divided by 3, which comes out as 0.359 newtons. And then K is what we're looking for. That's the spring constant, is F divided by extension, and so that is 0.359 divided by the extension of 0.01. And I've got 35.9 newtons per meter. I'll just do a wee double check there to make sure that that makes sense. So 35 newtons per meter, and so with a much smaller value here of weight, we're going to be dealing with 1/100th of the of that extension. So I think that seems reasonable. Okay, this was quite an interesting one on the ramp. It sort of seems more reminiscent of old level 1 physics questions. So compare both routes by considering the work done. So work done is, I would normally refer to it as energy. And so I would be looking at EP equals mgh. Mass is the same, gravitational field strength is the same, and the change in height is the same, regardless of whether you take the stairs or the ramp. And so the work done is consistent across either route. Okay, work done. And that's due to, as I say, EP equals mgh, and all of those values are the same. So the force required, and normally I'd be looking at using the work done is equal to force times distance here. Now this is an interesting one because you've got to consider whether you're considering just the vertical distance or whether you're considering a diagonal, in which case the ramp is longer. So if we assume that you're applying a force in this general direction or in this general direction, then the stairs would take a shorter route, which means that D is smaller. We know that work done is the same either way, and so if work done is the same and the distance is smaller, then the force must increase for the shorter distance route. So stairs require a higher force. And power is equal to the rate of change of energy. And so again, the energy is constant. The question says it takes less time to go up the ramp than the stairs. And so because the ramp has a smaller time and the energy is the same, if the denominator is smaller, that's going to lead to a larger power. So ramp, what would you say, requires increased power. Okay, or your power would be increased by taking the ramp because you're doing it in a short time. You're using the same energy over a short time. All right. The next question is your standard sort of equilibrium question. So the conditions required, we're looking at the sum of the forces upwards is equal to the sum of the forces downwards. And your second condition, you'll see plural conditions there, is that the sum of the clockwise torques is equal to the sum of the anti-clockwise torques. So our suitable calculations, so we've got a labeled diagram here. I'm just going to add to that. I'm going to call this string B and I'll call this string A. We've got, we need to remember the mass of the shelf is going to, halfway across, is going to provide us with a weight force of the shelf. And that's going to be 9.8 times the mass of the shelf, and the shelf is 0.37 kilograms. The ginger spice, I had to think about the Spice Girls while I was reading this question. So it's 0.15 meters away. It has a mass of 0.03 kilograms, and so our weight force there will be 0.03 times, well, negative 9.8, but I'm just going to call it 9.8 for the moment. And then 5 centimeters away from the left-hand edge is the sea salt, and that has a mass of 0.5 kilograms, which we multiply by 9.8 to get our force. So that is going to give us a force of, the sea salt is going to have a weight force Fw of 4.9 newtons. There's a decimal point there. The ginger spice is going to have a weight force of 0.294 newtons. And the weight of the shelf is going to be 3.724 newtons. I could have rounded these values, but I'm just going to work with those values as they are for the moment. So if I treat A as my pivot, then I know that the clockwise torques, which will be the torques exerted by the sea salt, the ginger spice, and the shelf, will, when added together, equal the anti-clockwise torque from B. And so that's the, I'll call the sea salt F1, just starting working from the left towards the right. So F1 times D1 plus F2 times D2, so that's the ginger spice, plus the shelf itself, so I'll call that F3 D3, is going to equal 0.40, I can even call it, which is the distance from A to B, times whatever support force B is providing. So we know all of these values, and so we can resolve this. So F1 was 4.9 newtons, multiply that by 0.05 meters, add that to 0.294 times 0.15, and then add that to 3.724 times 0.2, and we know that that equals 0.40 times FB. And so when we resolve that, that should give us 1.0339 is equal to 0.4, I'm just going to 0.40 times FB, and so FB is equal to 1.0339 divided by 0.40, which equals 2.58 or 2.6 newtons. So we know that support force B is 2.6 newtons. We don't need to do that to work out support force A. We can just use the sum of the torques. So we know, sum of the forces. So we know that the upwards forces, the total upwards force equals the total downwards force. The total downwards force is equal to 4.9 plus 0.294 plus 3.724, which equals 8.918 newtons. And so FA must be providing 8.918 minus whatever B was providing, which was 2.6, which is 6.3 newtons or thereabouts. Since this is greater than 5.0 newtons, the shelf will break or fall. Okay. Right, that brings us on to question 3. So here's a standard kinematics question. We have a VI of 0.56 meters per second. We've got a time of 4.0 seconds. We know it comes to a stop, and so we know that VF is 0. What's the acceleration? And so we should recognize that, or be able to find from the resource sheet, that we're going to use acceleration is equal to VF minus VI divided by the change in time. And so that is going to be negative 0 minus 0.56 divided by 4 seconds, 4.0 seconds, it doesn't make much difference. And so that's going to come out as negative 0.14 meters per second. The negative makes sense because it's if we're treating the 0.56 as positive, the acceleration is going to be in the opposite direction. Okay, then we are on to a projectile motion question. So vertical and horizontal components of the initial velocity. So if I got an angle of about 40 degrees there, sorry, that should be 40 degrees, and we've got 5 meters per second there. So the horizontal component of the velocity, VH, will equal 5 times cosine 40, and you could use SOHCAHTOA to work that out. And VV, the vertical velocity, it's going to be up here, is equal to 5 times sine 40. Okay, hopefully your calculator was in degrees and not radians, and that should come out at 3.8 meters per second and 3.2 meters per second. Just double checking that, 40 degrees would expect the horizontal to be slightly longer than the vertical, so that makes sense with our answers. What type of motion is it? I think they're probably looking for projectile motion there. And then if you've done some past exam questions, you're probably familiar with this sort of one. For points A, B, and C on the diagram, add labelled arrows of appropriate length. I might just use a finer pen for this. So the forces, if any, acting on the apple. Now, I feel like I need to assume something here, so I might just state assuming the apple has left the hand. Left the hand. And at C, that it's not yet struck the table, so it's immediately before it strikes the table. In which case, if the apple has left the hand, then we're going to be looking at a force, a weight force on the apple. So using you might want to use a measuring tool here, so I'll use 1 centimeter as my weight force. And then at B, I would be labeling on the weight force is not changed, and then C, again, a consistent weight force. So all of those are the same magnitude. Then the direction of velocity. I was wondering about whether we should be talking about friction with the forces. A little bit tricky, so it gets a bit complex, but technically projectile motion, a projectile is an object that's acting only under weight, and so I would not include friction for this, but if I wanted to include the frictional forces, then that's going to have quite a lot of implications to both of my answers. And I would be drawing, if it's left to hand, then there would be a frictional force acting against the direction of motion for A. There would be a horizontal frictional force for B, and there'd be a horizontal frictional force for C. Technically, they would be getting slightly smaller as time went on, because as the horizontal velocity decreased due to friction, then that frictional force is going to decrease as well, because the apple's not pushing through the same number of particles per second to provide that original frictional force. But I think that's probably overthinking what we're looking for here. So moving on to the direction of velocity. Well, A will have a... I'm in two minds. I could break these down into the horizontal and vertical components now, but I think because I'm going to be asked about that in part 3, I might just label that the direction of velocity is going to be that way. So that's combining a horizontal velocity and a vertical velocity. Interesting that they've kind of flipped the perspective. On this side it was coming to the left, and on this side it's coming to the right, but there you have it. B, there'll be no vertical velocity at B because it's at the apex, and so the direction of velocity is purely horizontal. And then at C, it should be really you should just be flipping that arrow around the horizontal to give you the direction of velocity at C, assuming that that is immediately before it impacts with the table. So I think that's what we're looking for there. Describe how the vertical velocity and horizontal velocity of the apple changed throughout the flight. Well, this should be a nice, easy question. We've got the horizontal velocity, assuming no friction, does not change, as there is no force or component of force in the horizontal direction. This answer would change if we were including friction, and if we were including friction, then we would be saying that the horizontal velocity would decrease over the journey of the apple as it slows down for the reasons that I mentioned earlier. For the vertical velocity, it starts as upwards, but is accelerating down throughout the journey at a rate of negative 9.8 meters per second squared, and so reaches zero velocity at apex, and it'll have at C, again, if we're ignoring friction, then we're dealing with, and we're not hitting terminal velocity or anything like that, then we're looking at, if it was vertically 3.2 meters per second at the start, then it's going to be negative 3.2 at the end, because it's fallen the same amount of height that it gained in reaching the apex. Okay, so I think that's what we're looking for there. Just double check the question. Describe how the vertical velocity and horizontal velocity of the apple changed throughout its flight. Yep. And that's all obviously due to forces, but it's only said describe, not explain. So I don't think I need to go on into more detail there. And then the last one is the ceiling is 1.5 meters above the table surface. Will the apple reach Tony, who's 2 meters away? And so what I'd be looking at here is how long is the apple in flight for? And so based on what I'd said a moment ago, we know that the time is going to be equal to VF minus VI divided by acceleration, which is negative 3.2 is the final vertical velocity, minus 3.2, the positive value there for the initial vertical velocity, divided by negative 9.8. That gives us negative 6.4 over negative 9.8, which is 0.65 seconds. That's going to be important for working out the horizontal distance. So the horizontal distance is equal to the horizontal velocity times time, which is equal to, what did I say, 3.8 times 0.65, which comes out as 2.47 meters. So assuming it doesn't hit the ceiling, it's potentially going to go past Tony. He may be able to move to catch it. For the vertical distance, I would use VF squared equals VI squared minus 2AD and rearrange that to give me VF squared minus VI squared divided by 2A. That's going to give us, at the apex, VF is 0, and then 0 squared is just going to be 0, minus VI squared, that was 3 point... Have I got my velocities around the wrong way? Horizontal was 3.8. No, that's right. And my... Yes, because I'm using the vertical ones to work out the time in the air. Yep, that all looks correct. Horizontal was 3.8, so I'm back to 3.2 here. Yep, 3.2 squared divided by 2 times negative 9.8. And so that should come out as negative 10.24 divided by negative 19.6, which equals 0.52 meters. So I think it's well clear of the ceiling, but it will potentially go further than Tony because it'll travel 2.47 meters. All right, hope that was helpful for you. Kakite.